So now, bang on time, 6:30, I'd pass over to Anna to introduce our technical presentation.
Awesome. Thank you, Roger. We are now moving to tech part of our meeting. And this evening, we're diving into innovative approaches in ventilation Louvre design, brought to you by Venture. We are honored to have Simon Hoyle, who is a director at Venture, as our presenter. In this session, he will focus on tips and techniques for achieving optimal balance between minimizing pressure loss, maximizing weather protection, and ensuring seamless integration with our building elements. So without further ado, please welcome Simon.
Thank you, Anna. And I must apologise in advance. My day is somewhat gone to custard, and right now I'm presenting from the Christchurch airport. So can you please let me know if the background noise is too bad? If you're not hearing me, then we might as well discontinue it. But if someone could just let me know how it's coming through.
Coming through nice and clear.
Yeah. Perfect. All right. Thanks very much. And yeah, apologies. This wasn't how I planned it to be, but look, we'll just kick off with the presentation. So thank you, Anna, for the introduction. Just to tell the team a little bit more about who we are and what we do. Venture is a manufacturer of ventilation and acoustic louvers. We've been going since the mid-2000s, formerly under a different brand by the name of Insol, and in 2019 the brand Venture came about, and we've been operating under that name ever since. We've got two branches. We've got a head office in Auckland, and we have a factory where all of our manufacturing is done down the South Island in Invercargill. We do a range of different products, all related to the ventilation of buildings, but the main ones we're going to focus on tonight are the ventilation louvers, and we'll touch briefly on acoustic louvers as well. I just wanted to show a couple of case studies of projects that we've done over the years. This one you see on the screen now was part of the Christchurch rebuild. It was the Burwood Hospital, and it included a large number of double bank louvers, single bank screening louvers, and for a plant room on the outskirts of the precinct, a number of acoustic louvers as well. I'll just skip over this one. This project here, forgive the renders, we haven't had photos taken of it yet, but it's the University of Waikato, the PAR, which some of you may have worked on. It's a fantastic building, entirely glulam timber structure, and we're privileged to have part of it in supplying our double bank louvers, triple bank louvers, and some smoke ventilators. So getting onto the subject of our presentation tonight, the basic principles of ventilation louvers. I'm sure we've got an experienced team here. A lot of you this will be second nature to you, but a louver is there to let air in or out of the building whilst keeping the rain out. And whilst we have some very high performing products, and I'll go into some of those in more detail shortly, it's important to note that no louver is ever going to be 100% watertight 100% of the time. By its very nature, a louver is full of holes. You have aluminium blades with gaps in between them. And even if you have a louver that provides 100% weather tightness under test conditions, we can't hope to test for every situation, every exigency. If we have some weather like we had last summer, Cyclone Gabrielle, for example, with huge amounts of rain, coupled with some fairly strong wind, there is a possibility that even a high-performing louver will let some water in to your building. And I don't want to start off on a negative note by saying that, but it's just something that we find that a lot of people don't really appreciate, particularly architects. They view a louver in the same light as they view a window, and that is it's a solid barrier. No water's going to get inside under any condition, and that's unfortunately not the case. With that out of the way, I'll move on to some more specifics about the product. We've got a couple of tools which, if you've got graduate engineers or young people coming up in your teams, these are great tools for them to be introduced to. There's typically 4 criteria points that you require when you're sizing or selecting a louver. They're listed on the screen here. You've got the direction of airflow. Louvers perform differently depending on whether the air's entering the louver or exhausting through the louver. You need to know your required level of rain defence. And by that, I mean, if this was a plant room with a fully tanked and drained floor, you could quite happily use a louver with a lower rain defence than if it was, let's say, ventilating an interior space or a stairwell where any water ingress could not only damage the building, but potentially be a health and safety hazard as well. You need to know the approximate size and proportions of the louver panel. Most of the time, the architect will give you that information. Or sorry, you as engineers would determine the size of the panel. The architect will most of the time tell you how tall it needs to be and how wide it needs to be to fit in with the other elements on the building. But it's important to note that the height of the louver has plays an important part in how the louver performs. So that bit of information is critical. We can't just work on so many square meters of louver per se. And then lastly, we need to know the volumetric airflow that's going through the louver. With our calculators, we work in cubic meters a second. I know a lot of people work in litres per second. It's not hard to do the conversion, but so those are the 4 elements. Moving into how we use that information to select a product. What you're seeing on the screen here is a louver selector tool that's posted on our website. And if you look, to be honest, if you've been in the game a few years, if you've worked on projects with louvers in the past, some of this will be pretty basic. But for a young graduate coming out of university, just starting to cut their teeth in the industry, this is a great tool for them to start with. And it simply takes that information that we talked about earlier. It asks you a bunch of multi-choice questions. You can see some samples of them there. And depending on the answers you select, the tool will ask you different questions and so on until you've answered, let's say, roughly 6 or 8 questions. And at the end of it, based on the answers you've supplied, it will recommend a product. Now, it's not entirely foolproof. It always pays to get a second opinion, but it's a great way to narrow down your options. There's a lot of different products out there, and it can be a bit bewildering if you don't really know what you're looking for. I should add that once it gives you that product, it also gives you, this is, as I said, it's hosted on our website. It gives you a link straight to the product page, and so you can download any technical data or drawings, etc. Once we get into more detailed design, and this is where I guess the more senior engineers spend their time, we have a louver calculator, which is an Excel-based tool. I'm more than happy to email this around after this presentation, or it's available for download directly off our website. And you enter the information such as your product type, dimensions of your louver panel, volumetric airflow, whether it's got bird mesh or insect mesh, backing on the rear of the panel, and it'll give you the metrics, the throat velocity, pressure loss, active free area, and rain defence characteristics. Now, if it's all right, I might just switch my screen and bring up a live copy of that calculator, just so I can do some demonstrating for you. And I'll show you some of the things that we consider important in the outputs. So the sample I'm putting in here is a BL2SD, which is our double bank drainable weather louver. I'll put in a nominal size of 1500 millimeters high. Let's go 2 meters wide. We could say that we're going to put in a volumetric flow of 5 cubic meters a second. That's pretty high. We'll drop that. No, that's okay. 5 meters a second. It's getting on the higher side, but we've got a face velocity, and so you can see this cell here is populated straight away. So this is another way to think of this face velocity, as if you had a duct coming up to the back of the louver, and the duct was the same size as the louver panel. That is the velocity of the air that would be passing through the duct. Over here, we select airflow direction. I'm going to select intake, just because it's top of the list. We can have 3 different options for backing screens. So a number of situations, the louvers would stand alone. There would be no backing screen, but most commonly they would have a bird mesh, which is for our product, an expanded aluminium mesh formed by stretching a piece of aluminium sheet with holes in it, very fine wires that are created, and it will keep any birds, rats, mice, any larger vermin out. If you're in a situation where you can't live with, or your client can't live with insects getting through, we have a second option for insect mesh. And the cool thing about this calculator, which we find a lot of people comment on, is the fact that you can select these options and it will give you the relative pressure loss. So in the early days, a lot of manufacturers just gave you the aerodynamic performance of the louver on its own, and an engineer would have to make their own assumption or calculations as to, if they were putting an ancillary on the rear, what impact that would have on the performance of the louver. We've built that into this calculator. So you can see there, if we select the bird mesh, you're 29 pascals. We select insect mesh, 31 pascals. Admittedly, not a large amount of difference, but particularly at high velocity, it's worth noting. Moving over to the other columns, the data we get. So this throat velocity, so column J in the calculator, is the speed at which the air passes between the louver blades. So if you've got a louver that has a lower free area percentage, if the blades are closer together, your throat velocity will increase over against the louver where the blades are more open. And this is a metric that a lot of people have been conditioned to keep below 2.5 meters a second, because they've grown up on a staple diet of single bank louvers that weren't particularly weatherproof. So I hear it a lot. I go around practices and people say, I always size louvers so their throat velocity is less than 2.5 meters a second, which is fantastic. It's good insurance, but it does mean that potentially your louver is size larger than it needs to be. And I'll come to that in a bit more detail. Next, column L here, we have active free area. So it's important to note that you don't have a fixed percentage of free area per louver model. The larger you make the panel or the smaller you make the panel, that free area is going to change. And I'll show you what I mean there. If we say that's 40% currently, and if we turn this louver into a small panel, let's go 300 millimeter square, ignore the pressure loss, I'll just leave that airflow as it was, but you can see that active free area has dropped substantially to 17%. Now, if you're scientific, if you're doing the maths properly, you don't really need to bother about the active free area. The numbers you need to consider are the air velocity and the pressure loss, because, as you probably know, free area doesn't necessarily equate to aerodynamic performance. It definitely has some correlation, but it's not directly related. The reason we've put this active free area column in our calculator is that we find fire engineers in particular will often use it in their sizing of louvers when they're using this sort of product as it's part of a smoke exhaust system. Over here, we have the predicted rain defense effectiveness, which for this product, you can see we've got 98.8%, which under the BSE and 130 classification is a class B. That's slightly more than 1% of the water is getting through the system under the test conditions, despite the fact we've got a throat velocity of over 4 meters a second. And that was what was behind my comment earlier about don't get too worried about this throat velocity. Yes, it can be high. Yes, for the cheaper products, for the single bank louvers, if you've got a high throat velocity, you will get a lot of water carryover. But there are some high performing products available, of which we've got a number, where you can have high airflows and still have limited water ingress. Over in the last columns, the 13030 classification has a class for the aerodynamic performance. In this case, it's a class 3. I haven't come across a lot of people specifying louvers using this class. Most people would specify an actual pressure loss maximum expressed as pascals, but it's there. It's part of the outputs from the test, so we put it into the calculator. And then last of all, we have a hyperlink here, which if you were to click on it, would take you through to the relevant product page on our website. Now I'm happy to take questions on this calculator at the end of the session, but just conscious of time, so I'll skip back to our presentation for now. So a couple of tips for where specific types of louvers shouldn't be used. There are products out there that are designed as exhaust louvers and are specifically designed for low pressure loss. They don't do a good job of keeping water at it, so don't use them in a situation where you're trying to prevent the rain from blowing inside. Non-drainable louvers for tall louver panels. So I mentioned the height of the louver being important in the selection earlier, and that's first and foremost from a weather protection perspective. There's two different types of louver. Generally speaking, you've got a system where the blades capture the water and it discharges down the front of the blade and lands on the blade below, and so on and so forth until it reaches the bottom of the panel and it can drain out. The second option is a drainable system where the blade has detail in the extrusion. It captures the water, which is drained out through channels and then down through gutters or downpipes in the frame. And it means that each louver blade is only ever dealing with the water that lands on itself. It's not dealing with runoff from other blades. But what that means is non-drainable louvers can be very effective for small louvers, low louvers, where that cascading effect doesn't compound and become extensive. But if you've got tall louvers, let's say you're above 1.5 meters high, 2 meters high, 3 meters high, if you're using a non-drainable system, by the time all that water is drained from the top blade all the way down, the bottom portion of the blades is going to be completely swamped, and you're going to get a lot of water ingress through that lower portion. And the last no-no, is using louvers with large blades or large frames for very small panels. And we saw an example of that earlier when I put in that 300mm square two-stage louver. You've got a louver system there that has a frame 60mm wide around the perimeter. So if you think about a louver that's 300mm wide overall, you've got 120mm. Your actual active area of louver in that 300mm panel is only 180mm in the middle. It seems an obvious mistake, but we do see it all too often, particularly where you've got an architect trying to squeeze a louver into a small space. There's a lot of text on this slide here. I won't read it out, but the long and short of it is that when you're selecting a louver, when you're playing with louvers, you can have a system with high rain defence, or you can have a system with fantastic airflow, and near the twain meet. There's not yet the perfect louver that combines both, although we're working on it. So it's important to determine from the start what matters for your project, whether it's that rain defence effectiveness or whether it's your aerodynamic performance is of greater importance. I'm just going to skip over that one. I won't spend a lot of time on this slide, but important to note that the louver system itself, when you're putting it into the calculator and when you're designing with it, you're working with proprietary product, and the data that you're working with is from a tested system that's been tested under certain conditions, and most of the time as it's on its own right without anything attached to it. If you're starting to add plenums to the back of the louver, if you're adding blanking panels, for example, vermin mesh, we do see filters as well for makeup systems or insulation. If you put insulated blanking panels on the back, all of those can affect the overall performance of your system. So just be careful. If you're in doubt as to whether what you're doing might affect the performance of your louver, feel free to reach out to us. Now, one thing we find a lot of engineers are interested in, even engineers that have worked with louvers for many years, is how the testing actually works. So they may have been specifying louvers as a Class A louver, a Class B louver, whatever it might be, but not necessarily understanding exactly how the product is tested or what that data even means. So this on the screen here is a quick snapshot of the BS EN 13030 test. You've got a louver in the centre of the test rig. It's 1 metre square. You've got a fan on the outside which blows air and water injected into the airstream through these rain nozzles here at the face of the louver. So that's simulating wind-driven rain. And then you've got a secondary fan on the back of the louver drawing air in, mimicking mechanical plant. The test is started with this rear fan turned off, so it's simulating a passive ventilating louver with just external influences. Any water that gets through is measured. The fan on the back is then turned on and sped up in increments of 0.5 of a cubic metre per second through that 1 square metre louver. And the more air you draw through, the more water gets carried through. And from that, you can determine the overall performance of the louver. A Class A louver is, under the test conditions, less than 1% of the water gets through the panels. Class B is less than 5%, so it's down to 95% effectiveness. Class C is down to 80%, and Class D is anything beyond that. So the general school of thought is once more than 20% of your rain has got through the louver, it's not a louver anymore, it's a sieve, or it's a decorative screen. And beyond that, the water ingress doesn't really matter because you need to have other measures in place to deal with it. It's important to note that this testing is all done independently. We have chosen to take our product to the UK to test in the BISRIA test lab under the BSE and 13030 test. There recently has been a company in Australia start testing. They built a rig to test to our local standard, which is the ASNZS 4740. The reality is the two test parameters are virtually identical. The way the product's tested is the same, and the way the data from the test is presented is also the same. So you can take a 4740 test, you can take a 13030 test, and consider them alike. There is a third test standard out there. There's the AMCA 500L, which is an American test. Completely different test, different data. Not saying it's a bad test, but the results it gives you are presented in a much different format to the way the 13030 test or the 4740 test is done. So if you're looking at products out of the States and you have been given data that looks like it's been done by an American standard, then just make sure you're treating with caution. Make sure you're comparing apples with apples. I'm going to skip over some of this and jump straight into some of our products. So really quickly, this, sorry, I'm just seeing my toolbar is still showing there. Sure why that's shown, but anyway, we'll carry on. So the first product is a triple bank system. So it's a horizontal blade louver. By triple bank, we mean there's 3 stages of blades, as you can see in this cross section over here. And until recently, that was the ultimate louver for our range and for our competitors as well. In terms of weather protection, if you wanted really good weather protection, you specified a 3-stage louver. Moving down the range, we have a double bank louver, which is very similar to the triple bank louver that we just looked at. You'll see it has the same primitive frame, same front blade. All it doesn't have is over here, you can see it has 1 blade at the back instead of 2. So you've only got the 2 blades. Still offers good rain defence, far superior to any single bank product, but just not quite as good as a triple bank system. Now this one here is a product that's we're forgive my proud dad speech, but we're really proud of it. It's a system that we've developed in the last 2 years. It's a vertical blade system. It's a double bank in that it's a chevron blade, although it's a single extrusion. But we've spent a lot of time and resource in developing this, and we're proud to say that it outperforms even the triple bank system in terms of rain defence, and it far outperforms the triple bank system in terms of aerodynamic performance. If there was one louver that we could say would be fit for virtually any project, it would be this one. The only difficulty we've got is there's a lot of preconceived ideas in the architectural world, and we find architects that consider a louver in their mind as something that has horizontal lines on it, and we introduce them something with a vertical line. Some of them like it. It's a little bit quirky, but all of them say, well, no, I want my louvers to be horizontal, thanks very much. If we turned this louver 90 degrees so the blades did run horizontally, we wouldn't get the same effect. It's just the way it's been designed. The other thing I just want to point out before we move on is the depth of the system. So you can see that it's 100 millimeters deep. It's much shallower than the double and triple bank systems we looked at earlier. And you can make it much smaller. It's got a much smaller perimeter frame, so you can make smaller panels and still maintain a reasonable level of free area. Conscious of time, so I'm just going to skip quickly over some of these. These are our single bank products. They have their uses in the right application. They're right for the job, but I guess the overarching thing that you need to be aware of is that any single bank product won't have the weathering performance of a double bank product or a triple bank product. If you're going to use a single bank system, make sure the room behind is drained, or you've got large catchment trays, properly designed plenums that are welded and sealed, and that any water that gets inside can't get where it shouldn't and cause damage. The baby of the range, it's our little slimline louver, commonly used for small kitchen exhausts or bathroom exhausts or louvered doors. Fits quite nicely into a lot of window suites. This one here is something that we pitch to architects in particular. It is a single bank drainable louver system, but it has the additional feature of a perforated facing panel. And you can see here on the screen there's 6 different patterns that can be chosen. The same blade type sits in behind. Now the cool thing about this, and what I want you to know about it, is that these 6 patterns have been fully tested to the 13030 test. We haven't just taken a piece of perforated metal and plugged it on the face of a louver and said, here you go. If your architect chooses a product like this, and we have test data, it's built into our calculator, you can work with these products, you can size them with the same level of confidence and accuracy that you can with all the rest of our systems. We also do a range of acoustic louvers. We have the 100 mil thick system. We have a 300, which is the most common product in our range, a common acoustic louver, should I say. We have a 450. As far as I'm aware, we're the only New Zealand manufacturer with a 450 millimeter deep system. And then last of all, for sort of maximum attenuation, we have a 600 mil deep system. Acoustic louvers work simply by having the blades formed with a shell around and then the interior filled with rock wool, so mineral wool. And you can see that in these renders here, with the orange being the rock wool, that absorbs the sound through perforations in the louver skin and prevents noise transfer through the wall. Now, the important thing to know about acoustic louvers is that they're, from an acoustic perspective, they're nothing like as good as a concrete wall. That might be obvious, but it's not always appreciated. And the smaller you can make your acoustic louver, the better acoustic performance you're going to get through your whole wall build-up. Let's say they are going into a simple precast wall. If you can make a hole and you can have a louver that's 500 mil square versus a louver that's a metre square, your overall noise transmission through that wall is going to be reduced. And where we pride ourselves on helping out is that our louvers have a low pressure loss compared to a lot of our competitors, which means that if you're when you're sizing it based on a certain airflow and a certain pressure loss restriction, you can make those louvers smaller, which means that your overall acoustic engineer is going to be happier with you. And sorry, sick joke at the end of the presentation, but we all have issues with cross ventilation from time to time. That brings me to the end of this slide deck. So I'd like to open the floor and ask for any questions. I'm just going to stop my screen share so I can see your faces again. And yeah, Anna, I guess I'd hand back over to you to unmute everyone.
Sure, if anyone has some questions, please raise your hand and I will unmute you. Thank you so much, Simon, for sharing useful tips for selecting louvers. I love your showcasing your calculator and all the products Venture can provide. And I'm sure this presentation showed everyone your expertise in the area, and I'm sure that we will now use this contact to, if anyone's stuck with selecting the product. I don't see any hands, so Roger.
Yes, Simon, how do you balance with your acoustic louvers water penetration? Because you said the blades are perforated.
Yeah, great question, Roger. So there's two answers, or two parts to that answer. The first is an acoustic louver. Neither Venture nor anyone else in the louver market at this point has a acoustic louver that offers fantastic rain defence effectiveness. It's just the nature of the beast that we deal with. If you're needing a high performance, high level of rain defence, as well as attenuation, then you're almost stuck with using a hybrid product where you could use a double bank louver and then an attenuator behind. We're doing a project like that at the moment, the Seascape Tower down on the Auckland waterfront, where exactly that's happening. There's facade louvers and then there's acoustic louvers behind to provide the attenuation. But your question about perforations, so the front of the louver blade, so that the part that's on the angle is solid. That's the part that captures the majority of the water. The fin out the back and down the underside is a shell of finely perforated sheet metal, and inside that you have the mineral wool, which provides the attenuation. If any water does get past that blade, the solid part of the blade, and lands on those perforations, it will sit on the top of the panel, on top of the louver blade, or it'll be carried through in the airstream. The beauty of the rock wool that we use, and one of the reasons that we use it, is it's very and forgive me, I can't remember quite the right term, but hydroscopic to an extent. It doesn't absorb water. You can take a piece of it and sit it in a bucket of water, and the water will only penetrate a few millimeters. It doesn't wick it up. So once the rain's passed, you've got air passing through, and it dries out relatively quickly, without creating too much, without causing any damage. But does that answer your question, Roger?
Yeah, no, that's great. Thank you very much indeed.